So today we'll be talking about sort of multiprocessing, and we'll do a bit of talking about like why we want to do multiprocessing, and it's essentially to apply it to cluster computing. So if you think back to, I think it's over a week ago now, we were talking about how the memory is organized in a process. So a single process has some memory to store all of the functions, like the instructions, some like constant data, and there's two sort of data structures called the stack and the heap that keep track of your variables over time. And last week in particular, we spoke about multithreading, which are represented by these squiggly lines. So a thread is like a unit of work that can be executed in parallel with one another. So if you have 4 threads and 4 CPUs, you can execute each of those threads at the same time. Those threads also have like a local stack as well. So like they need somewhere to keep track of their own variables local to the functions that they're calculating. We have sort of a memory here. Each stack has, each thread has a local stack, and all of the threads can access all of the memory within that process. So if something's on the heap, any of the threads can access that information. This had a few issues like race conditions that we had to come up with some ways to mitigate against sort of corrupting your own data, because 2 threads can read and write to the same place at the same time. Now, like I said, this is like your multi-threading paradigm. There are some issues with this though. And the main one being is the memory that you have access to is limited to the computer you're running on. And so a process can only sort of grow as big as the machine that it's running on. So in this case, if you have a computer with 16 cores, you can only really run 16 threads on that. You can't scale up beyond that boundary. And it's the same for memory as well. So if you only have 16 gigs of RAM on your computer, you can't put anything bigger than that unless you're like using a hard drive and things as well. So for really big problems, you need a different approach because this sort of won't cut it. And the idea is this isn't very scalable. It's really good if you've only got one computer available to you and you're trying to speed things up quickly. But if you're looking at really huge problems, we need to do something else. So this is where the multiprocessing paradigm comes in. So the idea is instead of just having one big process with all of the data and multiple threads, we instead split things up into sort of smaller processes and have many of them. Yeah, you can have as many processes as you want, basically. And the idea here is the boundaries of these processes mean that you can run them on different computers. So instead of just having a single computer running one process with 10 threads, you can have 10 computers, each running 10 processes, and have 100 processes instead in that case. So this is much more scalable. And the way that you can achieve this is instead of using the shared memory to communicate, you sort of abstract that away so that each process can communicate with each other, like send data between the processes and gather data together. So the way we can think about this is these A, B, and C's, just imagine them as different processes. It doesn't matter where those processes are, like which computers they are. But in order to sort of work together to solve a problem, you need to add in some communication between them. And so, so one way of doing this is having each process to be able to communicate with every other process. We call this a topology. So like how the processes are connected is just called the network topology. This one is like all-to-all. So every process can communicate with every other process. But the sort of most common one that you'll see is you'll have like a master worker topology where you have one sort of main sort of coordinating process, which can communicate with all of the worker processes, but the worker processes can only communicate with the main process. The sort of details of this sort of depend on your problem and what you actually want to achieve with it, but the word to look for is topology if you ever need to sort of research this in your own time. And so the main way of sort of abstracting away this communication is by using something called message passing. So message passing is just bundling up your data and sort of passing it between the processes. And this sort of communication can happen over any sort of network layers. So for example, if you have two computers on the same network connected by like Ethernet cables, you can use like TCP/IP communication. So it's just like standard internet networking to send those messages between them. The processes are on the same computer. You can just like communicate over like pipes and sockets, which is basically just a fast way to communicate between processes running on the same computer. You can, if you're on the same machine, have some like shared memory that lives outside of any one process, but that's not as common. Yeah. So basically the advantage to having this sort of abstraction, and it basically means you can run a problem on any number of machines that you have. So you can use all the resources that you have available, which gives you a lot of scalability. The main disadvantage of this approach, and why it's a bit lackluster if you only have one machine, is every process that you have has to have its own copy of its functions and its data and stacks and heaps. And any data that needs to be shared between processes has to be communicated via this message passing, which introduces a lot of latency. If one process has to wait, I don't know, like a second to get a packet from another machine instead of just reading it from its own memory, then that can introduce a huge performance difference when you compare it to something like multithreading, which is a lot faster. So one of the main ways in which you notice this is starting new processes introduces a lot of latency as well. So I don't know if any of you have used MATLAB before, but when you do parallelism in MATLAB, it uses like a multi-processing approach. So when you do your like parallel for loops, it will spin up multiple copies of MATLAB at the same time. And that takes, if you've got like 16 cores, that can take like 10, 20 minutes for it to actually open. And it uses a ton of RAM as well, because it has to load up a copy of like the MATLAB runtime for every single process. So yeah, if you've just got one computer, try to stick to multi-threading if you can. But if you've got access to multiple machines, then using multiprocessing is kind of your only option. So the main way in which languages take advantage of this is they use a standard called the message passing interface, or MPI. So this standard is implemented across the vast majority of languages. So you'll find them most commonly in like C and Fortran have big implementations, but also like Python has like a multiprocessing MPI implementation as well. So MPI implementations actually provide code that does the communication, like the networking, and it provides like a standard set of interfaces, so a standard set of functions that you can call in your code to facilitate this communication. And just to give you an idea, these are just some of the implementations that are out there. So there's a lot to choose from. Most commonly, people use like the OpenMPI, which is just like the open source version that tends to work pretty well across most hardware. And also MPI-CH as well is another one that's also open source. But particular supercomputers have really fast networking installed. So they're not like your standard Ethernet cables. They'll have like 100 gigabits per second interconnect, sometimes called like InfiniBand, which lets processors have really fast communication. And to take advantage of that like proprietary hardware, the vendors will write their own versions of MPI that use specifically that hardware. So if you ever get access to these supercomputers, it's probably worth using the correct MPI implementation to fully take advantage of everything you have. You can use it in Julia. The package is just called MPI.jl, and it's pretty much identical to the C implementation. So if you find any tutorials out there for the C version, it'll probably work the same in Julia as well. So the way an MPI program is sort of like the different parts of an MPI program is each process. So you can spin up like 10 processes across a load of different machines. Each of them will run the exact same program, so the exact same script. So every single process will run every line of this code. And the information about what each process does depends on sort of the label of each process. So in MPI, they use rank to sort of give an ID to each worker. So each of the programs sort of knows its own like name, its own label, and you can use that to basically coordinate the work between them with a bunch of if statements and things to say, if you're worker 1, do this code, if you're worker 2, do this other bit of code. And much like when we were talking about locks and like synchronization before in multi-threading, you can also use, they call it barriers here, to like synchronize the execution to say, make all processes wait at this particular line of code, this MPI.barrier, before moving on to the next block. And there's also commands for like sending information between the processes. So the 4 main operations are broadcast. So you have one process broadcasting your information to every other process. You have the opposite of that, which is a reduction. We've already seen that before, is like combining information together into a single value. And then there's these other 2 called scatter and gather. So scatter basically breaks up your information into chunks and designates where those chunks of information go to. So they each go to a different process. And gather is the same as scatter, just in reverse. I'm not going too much into detail on these because, as you can probably tell, MPI is a very sort of low-level library for doing these things. It's sort of very involved, very hands-on, and it takes quite a while to learn and actually get used to. It's necessary for the fast performance. So if you're ever sort of building a library or a set of tools for other people to use that really need the performance, then look into MPI as well. However, it takes a lot of time, right, to learn this thing, and you don't actually need to. So Julia has implemented like a standard library. It's called Distributed.jl, which gives very similar sort of functionality, but it's much easier to use. And we'll sort of go over using Distributed.jl. I just wanted to make you all aware that MPI exists. Yeah.
So implementation of MPI, or is it its own thing?
No, it's completely own thing. So it doesn't, I guess it draws on MPI for like inspiration because it's been around since like the 70s, I think, but this was created specifically for Julia. Yeah. This link at the bottom is a YouTube video that you can watch if you want to get more information on MPI. Okay. All right, so we'll go into some actual code. So hopefully this will start to make more sense. Okay, so everyone see this? I can make it a bit bigger if that's helpful. Okay, yeah. So here we just have some code to act as a sort of toy example. So this just runs like a Monte Carlo simulation that depends on some parameters. So essentially this is like a random walk, and it has some parameters that bias the random walk in one direction over another, and also the sigma is like a step size. The details aren't too important here. The important part is you're running some simulations and then you're saving some data from that simulation. So this is a pretty generic approach that you would use for most problems. So you have a set of parameters, you have some long-running simulation, and you want to check the parameters of that simulation for many different sort of input arguments. So many different walk lengths and biases and things like that. So if we just run this code, if you were to use this on like a single machine, you could just call the code by giving in some sort of very basic parameters. What you may not have seen before is structs. Structs is just like a group of data, just like putting data together, kind of like classes, but they don't have functions written for them. It's just a collection of data. And so this function will return one of these structs that basically says what are the parameters that you use to generate this data, and also some sort of results from the simulation. So in this case, it's just taking like the area under the curve and the list of positions as well. Again, this is just like a toy problem. It's not super important which ones come out. So the way this sort of simulation usually looks, or this is a really common approach when people want to use a cluster. Say this simulation takes 1 hour for one set of parameters. This one won't because it's a lot easier, but say one simulation takes an hour per time, but you have a set of parameters that you want to check the simulations for. So here there's 3 different warp lengths that we want to check, and then there's 1,000 sigma values for each of those warp lengths that we want to simulate as well, and there's a bunch of biases as well that we want to also check for each of the previous simulations. So the typical way of writing this would be, so I'm going to call it T, so for warp lengths, you iterate through that set, and then you create another for loop to iterate through your sigmas, and then you create another for loop to iterate through your biases, and then you run the simulation in some way using those values like T, sigma, and bias, and then you save to an array in some way. But as you can see, if you have, imagine you have like 10 parameters and you want to do like, call this like a grid search. If you want to do this, you're going to get very many nested if loops, and it's a bit hard to keep track of. So there's a nice function called product, which does the same thing as this sort of nested for loop and iterates through them. So I'll run that code and I'll show you what comes out. So if we have a look at this iterator, we have a big array that stores basically like tuples of those values. So this is the warp length, this is the sigma value, and this is the bias for each of these parameters. And it basically gives you every single combination or permutation of those parameters that you've specified. And let's say we want to run this simulation for all of these different parameter combinations. You can do this pretty easily with just using the map function. So you're mapping the parameter values to the simulation results. Here I use just an anonymous function to basically take the tuple, and instead of writing like args like 0, args 1, oh sorry, Julia's 1 base, args 1, args 2, like args 3, the ... or the splat operator will just sort of write that for you. It will just separate it out into the individual arguments. So I'll change that there. So yeah, as you can see, the simulation didn't actually take that long, but it will give you the simulation results for each of your input arguments. And again, you might want to do something a bit different. Instead of having all of your results, you just want to grab like one value out of it and do like a reduction. So one of the parameters here was the area parameter, but you can use the map reduce function as well, just to like work out what the average area was from your simulation. So this is pretty common. The only problem is when you have simulations that take an hour long each time, each of these maps will happen sequentially. So if you have like 10,000 elements, this will take 10,000 hours on your computer. So, and even if you use threads as well, and you only have 4 cores on your machine, that's still going to take like thousands of hours as well. So what you really want to do is take this and run it on the HPC instead. And to run it on the HPC, you need to use multiprocessing. So we'll take this code and transform it into a way that can use multiple processes. So I'll just create a new file. Yeah. And we'll start with the exact same code from before. So the first thing to do is we can call the distributed library. So I've already installed this, but if you haven't installed this, you can just write add distributed, and it will add the package for you. It is part of the standard library, so it should install like very quickly, but if you're getting errors saying can't find this library, you need to add it first. So once we add the distributed library, you might think we can go ahead and just start using it, but we need to actually spawn more processes to do the work for us. So there is a command called addprox, which will spawn new Julia processes and connect them together to make sure that they can communicate results. So one way of doing this on like a local machine, I'll say addprox 8, and that will spawn 8 new processes and wire up all the communication. You can also pass an argument called exe flags. So if I just open a terminal. So when you call Julia, you can give it flags. Like if you give it -- project, it will open the project of your current folder. Also, if you give the command -t or -- threads, you can set that equal to 1 to force it to only use one thread. So if you were to run this, for example, you can say threads.end threads is only 1 in that case. So equally with this addprox, you can use this exe flags just to control what arguments get sent to the new processes. So the important ones here is you want it to have access to all of your libraries. So all of the like distributed, or if you have plots or benchmarking, you want it to have access to all of the packages as well. So you activate the project, and also it's usually good to set the number of threads as well. You can have each process have its own threads as well. So you could have one process per machine you have, and have each of those processes use like 32 threads, for example. So you can mix and match these paradigms. They're not mutually exclusive. Here I'm only going to add 4 processes, so it takes a bit less time. So if I run this, you'll see this takes a fair bit of time. And what it does is it returns a list, and these are basically like the IDs of the workers that you just spawned. So there's a command workers, which will give you the list of IDs that are available. But this is on top of the REPL process, so the initial process that spawned them. So if you say the number of processes, you get 5, even though we added 4 workers, because you have one like main coordinator process and you have 4 workers. Everything clear up to that point? Okay. So once we've added the processes, we can start to use them in some ways. And the only problem is, actually, let's just run the code and see what comes out. So distributed, like map just uses like the serial implementation, just like a for loop, but distributed gives you a function pmap instead, which works almost exactly the same way, but instead of doing each loop sequentially, it will distribute the work out to each of the workers and sort of schedule it so that each element will be calculated in parallel, or each element of your array that you're passing will be calculated in parallel. So if we switch it to pmap and run it, we should expect an error, quite a big error that comes out. And you'll see here, it says that this Monte Carlo sim is not defined. Basically, it couldn't find that function. It just didn't exist on the worker processes. And so each new Julia process has to sort of compile and load the functions itself, because they have separate memory. It doesn't have access to the information that's in the main process. You need to make sure that that information is available on your workers as well. So here we've got all of our code inside this simulation.jl. It gives you the definition of the struct, and it also gives you the definition of the simulation function. So to make sure that it's available on every worker process, we use this @everywhere macro, which will take the code that you write on the right-hand side and run that on every single process in sort of global scope. So if we run that, we should now have access to, yeah, it all works because it can find the function and it will return it in the exact same way. So it executes each of these parameter sets on the workers, and then it gathers the results together into an array and returns that onto the main computer. So instead of like the MPI approach of like having to like work out how to communicate all of your data, this sort of abstracts away a lot of the details for you, and you can just think about your sort of maps and reductions. So our second thing that we wanted to do was just get like an average statistic, so like a reduction on our data. Unfortunately, there's not a nice command like pmap to do the reduction for you, but it's not too different. The syntax is just a bit strange. So this map reduce can be written in a for loop. So what we want to do is work out average area, and we're provided with this @distributed function, which, yeah, despite the name, is a map reduce basically. So the first argument you give it is the function that you want to use to do the reduction. So in this case, we just want to add all of the elements together. And then the second one, I called it args before. And then the second one is just a for loop, which is your map operation, basically. So whatever we do inside here will be equivalent to this function that we've written in the pmap there. So I am just going to copy and paste it. So this gives you the sim data. So this is the struct that was available before, and it has a field called area, which is what we're interested in. So we can get the area from that field by just doing simdata.area, and then we just want to return the final part of the map is just returning that area itself. And so what this function will do is it will perform a map reduce. So the map part is inside your for loop, and the plus function is your reduction here. So you can use a custom function if you want. So you could turn this into like a time symbol and do a product of each element, or you could write your own function that does a custom reduction between two types. So an example is like if you have histograms from each experiment and you want to combine them together, you can write a function that will combine the histograms in a sort of smart way and just return a single histogram with all the sort of data points collated together. So if we run this, yeah, we'll get the function out from before. And here I just divide by the number of iterations just to take an average. So this is equivalent to this map reduce line. It's the same thing, it's just a bit of a different syntax. So that's your bread and butter for using pmap, or for using the distributed library. I'd stick to just using this pmap and also reductions as well. And as we saw from before, these are quite powerful techniques. You can use this for a wide array of problems. If you want to do something a bit more specific, say you want to run like one process, you want to make sure one worker is doing this one specific task, there is a macro called spawn at as well. So we can say spawn at the worker process 4, and I want you to perform this Monte Carlo simulation with these parameters. And I'm just going to set that equal to a variable. So if you guys have done the task from last week, you'll have seen threads.atSpawn, which spawns a task to compute something, and then you have to await that task or fetch the results to actually use it. So it's the same here. So if we run this, it returns a type of future. And if any of you have ever done like asynchronous programming before, a future is just a result that isn't computed yet. So you get the results sometime in the future. And there is a function called fetch, which will look at a future, and it will just wait and block all execution until that result is received. And you and it returns whatever was returned from this side here. So we're going to say our answer is equal to that. And yeah, it just returns the struct containing all the information there. So spawn at is also a very useful macro. And there's other ones like remote call fetch. They're all basically the same thing as well. So one way in which I've used this in my own code is I have one worker that has access to like a database, and all of the other workers sort of start calculating results. And if they want to save checkpoints, they will use this spawn at function to call a function that saves sort of checkpoint information in the main database. Because if you have access to a database, you should only have one process reading and writing to it at the same time. Okay. Also, if you're doing this sort of simulation stuff, I'd recommend this package bson to do saving. So it's like binary JSON is what it stands for. And it basically just takes any data structure that you have and sort of serializes it and saves it onto a disk, which can be very, very useful. You can have custom types and things in there, and it will still work as well. And I think I had it in the old function, but you can load it in basically the same way. You just change the command round to loads, and you specify what you want to load out as well. Okay. All right. Any questions about this in particular? Great. So if we just go back to PowerPoint a second, we can start talking about actual clusters now, because this all happened just locally on one machine. So you can kind of think of a cluster as just a set of computers, and they kind of look like this in the image with the sort of racks and racks of machines. And so each sort of blade in that machine, so each individual unit is an individual computer, and they just put them like this to make sure they can compact it and make sure it takes up as little space as possible. So one of the sort of clusters that we have access to is Sulis, and this is shared between like Warwick and Birmingham and a few other places as well. This is not Sulis, the picture, but it's similar software, similar hardware even. So the reason we have access to this is because it has so many cores. This has over 25,000 compute cores. So it's more than you're going to get on any sort of desktop computer. Also has a bunch of GPUs as well. We'll talk about that more next week. So this can do around 2 petaflops. So your normal sort of computer is probably in the tens, maybe, of like gigaflops range. So this is like millions of times more capacity than you'd get on like your average laptop. So the reason I use this picture is each computer actually has 2 physical CPUs on the core. So this is called dual socket, and it has a ton of RAM as well. So there's a 0.5 terabyte of RAM per node. So if you're doing a problem that uses only, like 128 cores, then you could just use multithreading. You don't need to do multiprocessing. You could just ask for one compute node and run your job there. But if you were to need sort of thousands of cores, so Sulis, I think, lets you use 5,000 at the same time for like standard users. You need multiple machines. Also, it runs on Linux as well. So if you ever use or have access to one of these clusters, you'll have to learn a bit of Linux as well. Okay, we'll talk about the scheduler in a second. So the way that you actually connect to these clusters, you don't have to like physically go on site and like log into one of the computers there to use it. You access it basically over the internet or like through a network. So the sort of software that you use to connect to these computers is called SSH, stands for Secure Shell Host, and basically is a way of being able to connect to a remote machine. And so all of the communication is encrypted, hence the secure part of the name. And what it gives you access to is basically like a terminal. Like if you opened up like a command prompt on your computer, it's like being able to do that on the remote machine, and you can execute commands from there. Just a note, if any of you guys are doing this, you usually can't get access to them just on the internet, like at home. So you probably do need to connect to your university's VPN before you can access this. Yeah, so what you do is you SSH into the login node. So clusters have a special machine that's reserved just for letting users log in. And they do this so they can like manage their files and submit jobs to run on the actual computational nodes as well. So one thing to make very clear is don't use the login node to run your software. Like you submit a job and they run on the compute nodes instead. If you do this on Utilise, you will be banned. So try to avoid it. So yeah, so when we talk about submitting jobs, this is submitting jobs to the scheduler. So pretty much every HPC uses something called Slurm. It's an acronym for that, but apparently according to their website, they no longer use the acronym because they don't consider Slurm as being simple anymore. So it's just a Slurm now. It means nothing according to them. But it basically goes back to the days of when people had like a mainframe. So it's just one really big computer, but you had multiple users trying to sort of run their jobs at the same time. And so you have to come up with a scheduling system to let everyone get access to the resources that they need and make sure there's no sort of overlap or conflicts between them. And it gives you a set of isolated resources. So if you say, I want access to, let's say 60 cores on a machine and I need 200 gigabytes of RAM, it will block off that section of those resources for you so that no one else will interfere. So you won't ever run out of memory as long as you're staying below the 200 gigabyte limit. Yeah, well, we'll see more of this in a second. So I'll give you a demo or an example. So one more thing that will be probably new to most people who go into this system is these HPCs have to accommodate many different users across a wide range of domains. So the amount of software installed on these things is like in the tens of thousands. And all of these softwares all have conflicting version information. So the way that they manage this is by using something called an environment module. And it basically sections off an install of code to make sure that you'll only have access to that piece of software if you specifically request it, so that you don't have conflicts and installing one item breaks another install. Yeah, so the module command gives you access to that. So if you type into the terminal like module avail, it will show you all of the software that's available. If you do this on like a big HPC, this will take a while because there's, as I said, like tens of thousands. So there's another command called module spider. I don't know why it's isn't called just module search, but module spider lets you search for a specific piece of software. So for example, if you wanted Julia, you could say module spider Julia, and then it will show you which versions it has installed, and it gives you the full name so that you can use the module load command to bring it in. So the examples given here is you can load Julia 1.9, sort of check the version, it's all fine when you're just using the single Julia command. You can unload it and load a different version and then have access to that as well on the same machine without having to install something and uninstall something. Okay. Any software you need installed, usually you just ask the admin of the machine to install it for you. Okay. All right. Cool. So we'll go into another demo. And yeah, we'll go into him. So I'll just open up a normal terminal here, and we'll focus on this for now. So when you log in to a machine, the way you usually do it is you SSH, which is basically just a command. So you SSH, type your username, write the @ symbol like in an email address, and then you write like the name of the machine or the address of the machine. So this could be an IP address or it could be its host name. So for example, Sulis has this address for the login node. And then when you go to login, sometimes I'll have a password, sometimes I use keys. Read the documentation for the cluster that you're using, and it will tell you exactly how to do the connection. But when you log in, sometimes it takes a while if there are a lot of users there. Also note, they give you a big sign saying don't run computational jobs here, because yeah, you shouldn't do that. So the way that you can see what you have access to with Slurm, all of the commands start with an S, and then it's something that's obvious. So for example, thanks. The command sinfo will give you a list of all of the computational nodes that are available, and it will also tell you what state they're in. So mix means that some of the resources are being used, but some of them aren't. And alloc means all of the resources are being used. These are not available at all. And you can see some of the resources are idle as well. And on this particular machine, there's a lot of different partitions, and a partition is just a group of nodes available to do a certain task. And they have a special group of nodes that have GPUs in them. So not all of the computation nodes have access to GPUs, so you have to specifically request them.
How do I know if I'm currently in a login node?
On the login node, so you'll have to have SSH'd in, but you can see here, it says your username at login, whatever. Also, if you type in hostname, this is just like a normal Linux command, it will give you the name of the machine as well, so you can see where you are.
How can I change it? How can I change the node?
Change the node that you're logging into?
No, change the node such that I can actually do some computations.
Right, yeah. So in order to actually like run things, you have to use either the srun or more commonly the sbatch command. And what sbatch does is it gives you or you give it a file with commands that tell the scheduler what resources you want and also what commands you want to execute. So yeah.
Distributed look like it's all processed on the same machines. Is Slurm going to schedule those out to different machines to like create a virtual block of compute, or you have to create some code which splits off into different computers? Yeah,
you call the add-prox command slightly differently. So I'll show you that in a second. So this sbatch command, again, in the documentation, they have loads of these examples. But essentially, you put in these comments, they're called like directives, that tell the scheduler how many resources you want. So for example, it says, I want you to use 2 different computers. On each of these 2 different computers, I want you to run 4 tasks. So in this case, a task is a process. And I want each of those processes to be allocated 2 CPU cores as well. The memory is usually, I think, memory, I'll put that per task. Yeah.
Are those multi-threaded cores, or is it like virtual cores?
Like multi-threaded cores, yeah. So those CPUs per task will be on the same machine, or they should be. If you put that to more CPUs than are available on a single machine, it should give you an error as well. So what's really important for scheduling is you have to specify a maximum time limit, or else your code just won't get scheduled at all. So if you sort of have an intuition for how long your code will take, and you give a limit with some padding, just in case there's some slowdown, you'll be able to get your jobs in much faster, because you're saying to the scheduler, this will only take 5 minutes, and so it's easier for it to fit that into the overall schedule. You also have to specify the partition that you're running it on, and so you get the partition just from that sinfo command, which doesn't look as good there. So yeah, no questions. So yeah, on here, I logged into Sulis, but I won't be doing the demonstration on Sulis because it can take a while to submit jobs. You might have to wait like 10 minutes for it to actually start running. So I'll exit from there. So instead, I'm using Orpheus, which is our in-house cluster that we have here in physics. It's only got 3 machines on it, so it's not a huge one. So you can actually see what people are running by using the SQ command. And you can see there's one person running a job on here. And on these big machines, usually there are so many jobs that you can't actually find your own job and like how long it's taking. So you can use this -u and your username to sort of filter only to your jobs. Currently, there's nothing running. So let's change that. So again, we specified all the resources we want. We've used the module system to load the correct version of Julia that we want to use. So we have access to this Julia command. And then we're basically just running this file, distributed example. So if I open this file, there's not much new here. All I'm doing is defining a function getInfo, which basically just creates a dictionary with the number of threads on that machine, like the name and also the ID. The only thing that's changed is we're using this cluster managers package, which provides some standard implementations for using the common clusters. So Slurm is probably the one that you'll be using on yours, but there are others. So all you're doing is instead of saying just 8 processors, you pass it Slurm manager, open brackets 8. And so it passes it to Slurm to create the processes instead. So, and it knows where to put those processes based on some environment variables that are set by the scheduler when your job runs. And the reason I'm saying 4 here is because I've selected 2 nodes and then 4 tasks per node, so there's going to be 8 processes. Again, we can use this exe flags to say I want 2 threads available per process as well. And again, we use this project just so it has access to all of your packages. So all this is going to do is it's going to define the function everywhere, or add the processes, define the function, and then it's just going to use the spawnat command just to get the info and then print it out to the standard output. And when you submit a Slurm job, you don't have access to like the console output. It will save that to a file instead. So we'll run this and then see what comes out. So the way we run is by using this sbatch command. And then we give it the name of the file that contains everything. And so usually you give it just a bash script like this. So if I'll just change that back. Yeah, so when you submit a job, it will give you an ID, and you can see when that's running as well. So on, let me just. Okay, so here you can see the job is running and how long it takes. Once it's finished, it will exit from that screen. And what you will notice in your files along the side is the output is saved in like a .out file. It's just a text file. There's nothing special about it. But you can see the results from each of the workers are sort of printed in order, just like was in the original script. You will notice this at the front. So when you run the addprox command, it will print out this connecting to each of the workers. And you can see, because we specified 2 nodes, there's actually 2 different computers running this program. And they're able to communicate because they can find each other over the network. So when your admins set up your cluster, they'll set up all of the communication stuff for you. Okay, so I think I'll leave this there. All of this code I'll put up in a GitHub repository and I'll link it on the website as well. I'm not getting too into detail because most of the parallel programming techniques that you learned before can be applied here. You just have to change the syntax of which functions you're calling. But the main idea is, or the main things I encourage you to use are the pmap command and the @distributed macro for doing reductions as well. And that should be everything. Are there any questions?